Every few years, the Mathematical Association of America publishes the latest edition of the contest problem book, which consists of the previous year's AMCs with the official MAA solutions. So I decided to purchase the very first edition of this book so we could look at the very first AMC. Over the course of its history, the AMC has undergone a number of changes over the years. In the beginning, these contests were called the American High School Mathematics Examinations, abbreviated as ASME. Now they are called the American Mathematics Competitions. The ASME has been replaced with the AMC 10 and 12, and there was also a middle school version of the contest called the AMC 8. Now students have 1 hour and 15 minutes to complete the 25 questions on the AMC 10 or 12. The 1950 exam I found consists of 50 questions, but I was unable to determine what time limit there was, if any. The scoring system for both exams were different. Current exams are scored with 6 points for each correct problem and 1.5 points for each answer left blank. In 1950, the 50 questions were divided into 3 parts. Part 1, Part 2, and Part 3. Each question were awarded 2, 3, or 4 points. What hasn't changed from then to now is it's always been multiple choice out of 5 options. In my brief scan of the problems in the 1950 exam, I haven't seen too many differences between then and a current AMC. So let's focus instead on the final 5. In the 1950 exam, the final 5 begins with problem number 46. You can also find these problems and the rest of the problems in the 1950 exam on the AOPS website. In this problem, we're given this triangle with these 3 side lengths, and we're going to double the lengths of 2 of these. So AB will become 24, and AC is replaced with length 14, and BC remains the same length. Scanning these answer choices, I don't think the area is going to change in the way it's described, either doubled or multiplied by 4, unless we have a right triangle, which we don't. I'm intrigued by this last answer option. A triangle with an area of 0 is a degenerate triangle, which leads me to wonder if the triangle inequality is satisfied here. This has that if we have 3 side lengths of our triangle, A, B, and C, with A being the smallest side length, then we must have the sum of the 2 smaller side lengths exceeds the length of the third. In our new triangle, our 3 side lengths, 10, 14, and 24, when we sum the lengths of the 2 smallest side lengths, we get a length that's equal to the third side. This is indeed a degenerate triangle, and our answer option is E. Let's go on to the next final 5 problem, number 47. Let's draw this triangle again, and we have a rectangle that's inscribed in it. We'll label some of these lengths, starting with the base of the triangle is B, and the altitude is H. The altitude of the rectangle is half of the base. They're calling this X. If I let W be the width of this rectangle, then X is W over 2. I want to find a relationship between X and B and H. I'll start by noting that triangle ABC is similar to the bigger triangle ADE, and we'll take advantage of the corresponding sides. I can find the height of triangle ABC in terms of some of these variables. That's going to be the height of the bigger triangle H, and then I'll subtract X. So if I compare the heights of these 2 triangles, the height of triangle ABC, which is H minus X, over the height of the bigger triangle, which is H. I can compare these to the corresponding sides of their bases, which are BC and DE. BC is the width of our rectangle, which I have called W, and DE is B. We don't want W in our equation, so we can write it in terms of X. This is 2X. And now we can solve for X and hope it's one of the answer choices. First, we'll multiply by the denominators, collect all the X terms on one side, factor out the X, and isolate the X. Let's look at our answer choices, and it's option C. Let's go on to problem 48. And here we have another triangle. This time it's an equilateral triangle. And we're going to pick a point at random inside the triangle and drop 3 perpendiculars to the 3 sides. Let's call these lengths H1, H2, and H3. And we're asked to figure out which of these 5 options is equivalent to the sum of our 3 perpendiculars. This actually looks like Viviani's theorem, which states that the sum of these 3 lengths is actually equal to the height of the whole triangle. If you're not familiar with this theorem, it's easy to show by drawing lines from our point to the 3 vertices of our triangle. If we call our chosen point P and the vertices are A, B, C, then we can express the area of the whole triangle in terms of the sum of these 3 smaller triangles. triangle APC on the left, triangle BPC on bottom, and triangle APB on the right. The area of the equilateral triangle, if it has a side length of S, is 1/2 S times H, which I'm calling the height of this equilateral triangle. On the right-hand side, the area of triangle APC is 1/2 S times H1, BPC is 1/2 S H2, and APB is 1/2 S H3. We'll multiply the whole thing by 2 and divide by S, and we get this. And that is option C. Let's go on to 49. So far, these problems seem easier than what you would see on a typical Final 5 on recent exams. We also don't see locus problems so much anymore. Let's start by putting these points on the coordinate axes. We'll put A at the origin, which means B is 2 units to the right. Since the median is 1.5 inches long, I'm going to define this point M to be the set of points that are a distance of 3/2 from this point A. All of these points are going to form a circle. If we give the coordinates of our point M, if we call them P and Q, then they satisfy our circle equation for a circle centered at the origin with a radius of 3/2. That gives us p squared plus q squared equals 9/4. This point is also going to be the midpoint between B and C. We're interested in the locus of these points C. Since M is the midpoint between B and C, P and Q are the average of the x and y coordinates of these 2 points. So P is 1/2 x plus 2, and the y coordinate Q is 1/2 y plus 0. Both of these equations must be satisfied, so let's make our substitution so we can find out what this equation is in terms of x and y. Substituting for P, we get 1/4 times the square of x plus 2, and for Q, that's 1/4 y squared. Multiplying by 4, this looks like a circle with center -1, 0 and a radius of 3/2. We eliminate these 3 because the radius is wrong. It's not an ellipse. Checking D. Oh, I made a mistake. I forgot to multiply this radius 9/4 by 4 to get 9. So this radius is actually 3. That matches with this. If the center is at -2, 0, this is a distance of 4 from our point B. So our answer is D. Let's go on to the last problem. This is a funny problem because it includes a lot of extraneous information with vocabulary a student might not recognize and potentially throw them off. You won't see something like this these days, but let's do the best we can. A privateer is basically a pirate ship or maybe a warship. I guess a merchantman is just a regular ship conducting its business. Leeward, I think, means just downwind. I believe this is mentioned because at some point the sail is lost, and so that slows down the pirate ship. So let's parse this problem. We start off at 11:45 a.m. with our pirate ship and our merchant ship 10 miles apart. It looks like we're to interpret this to mean that the pirate ship is moving at 11 miles per hour, while the merchant ship only goes at 8 miles per hour. And then we have this 2-hour chase. So now it's 1:45 p.m. The difference in the rates between the pirate and the merchant ships is 3 miles per hour. So every hour, the pirate ship gains 3 miles on the merchant ship. So now somewhere downstream, after 2 hours have elapsed, the pirate ship has gained 6 miles on the merchant ship. So we'll subtract that from the 10 miles where they started off, and now they're only 4 miles apart. But now something has happened to the sail of the pirate ship, and it says she can now make only 17 miles while the merchant ship makes 15. So I take this to mean that in the same time it takes for the pirate to travel 17 miles, the other ship can only go 15 miles. So the ratio of the speeds of the pirate ship and the merchant ship are 17 to 15. We want to see how long it takes the pirate ship to catch up to the merchant ship in these remaining 4 miles. I want to subtract the rates again between these two ships. So I'll substitute for RP. Oh, but the merchant ship is still traveling at the same speed, 8 miles an hour. That hasn't changed. So we can substitute that in for RM. And simplifying, we get the difference in the rates is 16 over 15. Time is equal to distance over rate. This difference in the rates is equivalent to the merchant ship being still in the water and the pirate ship traveling at 16 over 15. So we can substitute 4 miles for the distance and divide by this rate, 16 over 15. This is 15 over 4 hours. We'll write it as a mixed number and then convert this into minutes. So this remaining chase takes 3 hours and 45 minutes, starting at 1:45. So we'll add that time. That's 4 hours and 90 minutes. We'll pull out 60 minutes and call it an hour. So that's 5:30 p.m. Let's check our answer choices. That's option E. I think it's pretty clear that these problems are more straightforward than what you would see on a Final 5 on a current AMC. You can find more of these old problems at the AOPS website, or you can purchase one of those contest problem books. If you'd like me to solve any other contest problem, please leave it in the comments.